All right. So the notes were posted about 12 minutes ago, and I'm sorry. I'm falling behind. I don't know. Okay. So today's the third lecture of Chapter 8. Just about going to finish it today. I'm going to send out a few more discussion questions that will add to the discussion questions you already have. These will be ones that we go over for calculating delta G. That's what we're going to talk about today. So I hope everybody brought a calculator, plenty of paper and a pencil, because we're going to do more and more of this problem stuff, all right? So don't panic, folks, if even though the notes were posted, within the last half of an hour, I've made some changes, okay? So just some stuff moved from one place to another. So there's only one thing that's new, okay? So don't panic. All right, let's move on. So I want an honest show of hands. Honest, honest, honest. How many of you think you are very good at determining if something is spontaneous or not? Raise your hand. Okay. I'm not either. Okay. If there's a ball at the top of the stairs, yes, a little kick makes it spontaneous, and then it doesn't go back uphill. That's irreversible. I need to pick up the ball and take it back up, okay, in order to make it work. Okay, in order to get that ball back up there, it'll come this way, it won't go that way. That I can see as spontaneous, but several of you have asked me, well, how do we know if it's spontaneous? And I will say sometimes I'm not quite sure, okay? So today I've got good news for you. So, if we look at this situation here, we've got hot, we've got cold, we've got a bunch of balls on one side, and we've got some sort of an insulator here, we've got a little gateway there. We go from, this side went from hot to warm, this side went from nothing to warm, or cold to warm. In this case, we go here. The reverse isn't going to happen, okay? It just doesn't happen. So I'm just going to rush through these things. So we have learned this. We did this calculation. We didn't really prove this, but this is in fact the case, that the delta S is equal to the heat, reversible. That is the heat right there over the temperature, absolute temperature, okay? And in this case, it's just that the delta S of the hot one plus the delta S of the cold one is greater than 0. Anytime you have a spontaneous reaction, okay, your delta S total is greater than 0, all right? If it's reversible, it's equal to 0. Now, we also have statistical stuff. We went through this thing with microsystems, okay? So this is another way that we can look at entropy. So we got two ways to figure out entropy. One is a statistical way of entropy, and one is more of a heat way with using enthalpy. Okay, the problem, folks, is this, is that you can look in the back of the book, or in Appendix 2A, and there are delta H's of things, okay? And delta H is the heat. That's what it is. It's the heat that's given off. But that doesn't always tell you whether something is spontaneous or not. And then we have our entropy, which is not always so easy to tell whether something got more entropy or not. So we got a bit of a dilemma. So once again, you've got the surroundings, you've got the system, and then you got the whole universe. And you can never go backwards, okay? You either have a spontaneous reversible, which is the delta S total is greater than 0 at equilibrium, and reversible, it is equal to 0, and this just isn't possible. But folks, I have a hard time knowing what's not possible, okay? Because I'm not very good at determining whether the delta S of the whole universe has gone up or not, okay? And so we need an easier, at least Don Blake needs an easier way of telling whether something is spontaneous. The good news is that Willard Gibbs felt the same way, okay? So Willard Gibbs said, we need to come up with some sort of a mathematical term that will allow us to determine whether something really is spontaneous or not. A quantity, and not one that is somewhat abstract like delta total, delta S total. I'm just gonna, you have this in your notes, okay? I'm gonna just go to the end. So what Willard Gibbs came up with was this, okay? This is the Gibbs free energy. Write it down. You will need to know this backwards and forwards. Up and down, in and out. This you need to know. Delta G is equal to delta H minus T delta S. And all these little zeros mean here, folks, is at standard conditions, okay? And that's what they're given right here. And you have this in your notes. At standard conditions, which means 1 atmosphere, 1 molar, and pure solid, pure liquid. And why is it this way? Willard Gibbs says, you know, I live in a world that has 1 atmosphere, a world that is usually at around 25 degrees C. I don't want somebody, it's like buying a car, okay? You buy a car and they say, okay, the delta H is equal to 30 miles per gallon, okay? But you happen to live in New York City. Are you going to get 30 miles per gallon in New York City sitting in traffic? No. You need to know what kind of mileage are you going to get. So what Gibbs free energy tells us is, okay, this is how much energy you can get off in terms of heat. This is how much energy you have in terms of entropy. And then you have these two together, and that gives you delta G. Delta G is the actual energy you get, usable energy. Okay? Take into consideration these two state functions. All right? So delta G is equal to delta H minus T delta S. Know it, know it, know it. All right? This is new. Okay, I just put this in today, so you might want to at least watch this. Same equation. Okay? 2 SO2 gas plus an O2 gas goes to 2 SO3 gases. Okay? Now, I want you folks to at least have a clue as to what the sign should be for entropy. You can't look at, I can't look at something and tell what the delta H is going to be, unless it's a combustion, and I know it's going to be a negative number. But for entropy, folks, gases, we love gases because they have a lot of disorder. So a rule of thumb is that if you count the number of moles of gas on the reactant side and the product side, then if the product side has more moles of gas than the reactant side, then the entropy is positive. If you go the other way, if it gets smaller, then it's negative. Negative entropy is bad, okay? At least for a reaction. So look at this at first. How many molecules of gas do we have on the left side? We got a coefficient of 2, we got 2, 3 on this side, we only got 2 on this side. So what do you think the entropy is doing? Look at this, you got this many degrees of freedom and now you got this many. So it has decreased, okay? So in terms of the delta G, which once again, delta G was equal to delta H minus T delta S, don't forget, a negative delta G is what tells us that we've got energies. That it's going to be spontaneous. A negative value for delta G means spontaneous. That is almost a guaranteed question on the exam. A negative value for delta G means it is spontaneous. Look at this equation, folks. There's 2 ways you can make delta G negative. Okay? We have 2 things. We got delta H and we got delta S. You notice this has a minus right there. So if you want delta G to be a minus, how can we make delta G a minus? We could have a big negative delta H, right? If this is a huge, huge delta H negative, this is going to be negative. What happens if delta S is a negative? Ooh, that's bad. Because a negative times a negative is a positive. So that means this part's going to be positive. So you do not want that. So for a reaction to be spontaneous, you want to, I mean, you don't have to have a negative delta H, but you have a negative here, and if this is a positive, this is always going to be. There's no way at any temperature you're ever going to have a delta G that's not spontaneous. So I'm going to just be quiet and for about 30 seconds. I'm going to say what I said one more time, and then I want you to look at this equation and convince yourself that that's true. If this is spontaneous when it's negative, then if this is a negative, and this whole thing here, including that negative sign, is a negative, then it's going to be a negative plus a negative gives you a negative. If this is a negative, but the delta S is negative, then it's a negative for this times that, which is a positive. So this part is a positive. So if this part is positive, then that doesn't help this thing be negative. So convince yourself of that. Okay, so now you're convinced. Now do this problem, okay? What is the delta G at standard conditions of this reaction at 1 atmosphere? So we didn't have to say, I didn't have to say 1 atmosphere and 25 degrees C, because that's what that little thing means. Okay, that means, that little 0 up there means at standard conditions. So, and 1 atmosphere and 25 degrees. This is the world we live in. Okay? If the world, folks, if we lived in a world where the average temperature was 10 degrees, then all these things would be recalculated for 10 degrees. But 25 degrees is about average, and that's what the world we live in. Okay? So, I want you to calculate what is delta G using these. Okay? Products minus reactants. You notice that the oxygen is free. There is no delta H, okay? It's a freebie. It's free, okay? So first thing we calculate delta, we got two things we got to calculate, don't we? Okay, we have two things. We got to come up with the delta H for the reaction and this delta S. So we've got the product, which is 2 SO3s. Value is right there, minus 396. You got a value of 2 for the coefficient. So you got 2 times minus 396 here. And then you've got 2 SO2s, and SO2 is at 297. So it's going to be minus this. Okay, so that's what the delta H is going to equal. There is no oxygen because oxygen's delta H is 0. So what is this value, folks? Negative what? 198. Okay. So if we agree with that, if the delta H for this reaction is minus 198 kilojoules per mole, minus 198, is that good for a good minus sign for delta G? Absolutely. You got a big minus sign for delta H, very good chance it's going to be spontaneous. Okay? Because look at that. Now we got a substantial negative value there, almost negative 200 kilojoules. All right? So, what did we say was going to be the sign of entropy here? Just by looking at it. We're going from 3 moles to 2. That's not good. So I'm betting, I hope I'm right, that the entropy, the sign of entropy is going to be a negative. Let's do it and see. Okay? Figure out what is the delta S for this reaction. And folks, don't sit there and let me do it or your neighbor do it. You do it. Yes? Okay, good question. So folks, it's not me being mean. It's not me being mean that these are listed in kilojoules and these are in joules. The reason these are in joules, look at how small they are. Okay? This is less than a kilojoule. This is a lot of kilojoules. So you absolutely must convert, and I don't care which it is. I don't care if you go to kilojoules for this, or if you turn this into joules. You're going to get the answer right regardless. But you cannot add a kilojoule to a joule. Okay? So, do we have an answer? How many got that? Quite straightforward. A few more seconds here. Not long. Okay, do we get it? Yes. Loud.
Why is it minus 2 on 5 instead of plus 2?
Why should it be minus? Why do you have a problem with that? No. It can be positive or negative. Delta F, okay. I told you it was going to be negative. Right? Look at this. We went from 3 molecules to 2. I predicted it would be a negative delta S. Okay? Because we have more order, this has more order than this. Oh, in my equation. Oh, so you're saying I screwed something up. That's possible.
You just carry through the negative sign.
This is right.
It's fine.
This is right. It's a negative value. So, does anybody else have that question? You wonder why it's negative?
Why is the 2 and 5 negative?
Is that because that you dropped the parentheses and distributed the negative?
It's just a negative and a negative.
Yeah, it's just carried through.
This is right. Okay, it's just my way of doing math. Okay. Does anybody? Who got what I got? Raise your hand. Okay, good. Okay. I mean, I don't have a lot of confidence, so. So the point is that look, it's a this. This is the positive side, the negative and the negative. Okay. Products minus reactants. This was a reactant. This was a reactant. Okay. So we have a negative delta S. Okay? Is that good for a reaction? No. Because what if you put a negative right there? A negative and a negative is a positive. So that means, folks, that this is going to make this less negative. Okay? Now the good news, folks, is look at these numbers are similar in size, but this is in joules. Okay? So it's not going to cause this to go, if this is a big negative, this is not going to cause this to go positive until you get to a certain temperature. There it is. Still, delta G is minus 142 kilojoules. That's pretty darn negative, okay? How many think they understand this? How many are completely clueless? Okay, good. Okay, so let me ask you a question. Okay? So I'm telling you that this is minus 142 kilojoules. Is this spontaneous? Okay. I want you now to tell me at what temperature, what minimum temperature, will this reaction not be spontaneous? Simple question, simple answer. At what temperature will this reaction not be spontaneous? Or let's say where it's at equilibrium. That means this is a 0. So folks, this is simple, simple math. And if this kind of math get you worried, then you better go back and review your math book, because this is, once again, this is very simple stuff. Now I see folks on their cell phones, I see folks sleeping, I see folks not writing. I don't understand. Yes? Oh, I don't know.
Wondering, how did you cancel the moles?
How did I cancel the moles?
Yeah, because it says kilojoules every year.
Yeah, but this, okay, this is on a molar basis here. This is a mole, I mean, once again, if I don't give you a value, this means you need 2 moles of this, 1 mole of this to make 2 moles of that. So the moles are gone. Who's got an answer? You in the back, you. Loud. 1,059 Kelvin. How many got that? Oh, good. So folks, all you have to do, look at this. This is our adjuster right here. Okay, that T tells us that if this whole thing is, if this is a negative here, then we can make something not be spontaneous just by heating up the temperature. Okay? So anyway, this is an equation you got to know. This is not in the notes, but I hope you wrote it down. All right, back to the stuff I was given by your book. I don't think I understand this, but okay. So if delta H is negative as opposed to positive, so the green is good. If the delta S is positive, then if you have these two, it's always going to be negative delta H, or delta G. Okay, once again, if you got a negative value minus a positive value, those are 2 negatives. And delta G then is always going to be negative. Okay, we just did this. So here's a little bit of this is just a little, I want you to be comfortable with this, okay? So once again, this is delta H this way, this is delta S this way. So if, just look at this. Let me get it all. So what this is saying, that at high temperatures, low temperatures, all temperatures, okay, look at this. If a delta H is a negative and a delta S is a positive, it doesn't matter what temperature you're at, delta G in this equation has got to be negative. Okay? But what we learned just a minute ago was you can take something that is at room temperature is spontaneous, okay, but if the delta S is negative, it may be that you can get a negative delta G at low temperature, but at high temperature you're not going to get it. So this is just like a little, I mean, I don't even think this is a big deal. Let me see if it's got, I think it's got a bunch of other stuff in here. Oh, I don't know where that came from. Yeah, it's like holdover DNA or something, I don't know. Okay, it's in your notes. It's just a little thing. I'd rather you look at the equation, folks. I'd rather you understand that equation that delta G is equal to delta H minus T delta S, and you can just play around and figure out, for crying out loud, under what conditions are you going to have a negative delta G, and in which conditions you're going to have a positive delta G. At the triple point, right there, carbon dioxide, solid, liquid, and gas are all at equilibrium. Okay, equilibrium. Which of the following is true for the liquid to solid transition? And this is for the system. This is the system, okay? So, going from the liquid to solid, what happens when you go from a liquid to a solid? Okay, so here we are. Liquid to solid. We're doing this, okay? What happens to this liquid water? What does it do when it goes from a liquid to a solid? It gives off that 6 kilojoules of energy per mole that Don Blake can't see, okay? But it's giving off, and so guess what? Does this look at the delta S. Gooey, liquidy stuff like this, which has a little bit of entropy, going to some solid rigid thing. What do you think is happening to the entropy? Entropy is becoming more negative, right? Okay, and so which of these do you think is right? Once again, we're looking at the system. We're looking at the water right there. And the answer is the system is negative. Okay? Do we understand that? Now, I thought this was a trick question until I read it more closely. Looks like the same exact question. Okay? We're at equilibrium, blah, 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 blah. And then it says at the triple point, but then I realized that this is not saying the delta S of the system. It's the delta S of the universe. Okay? Folks, at equilibrium, the delta S of the universe equals 0. At equilibrium, delta G equals 0. At equilibrium, delta S is equal to 0. S of the total of the universe, okay? Not of the system, not of the surroundings, but of the whole universe. And this is the one where I have a hard time seeing that. And so that's why delta G is nice. Because if delta G is equal to 0, you're at equilibrium. Oh, okay, yeah, this is just going to show you that you got delta, everything is balanced, okay? Because we're at equilibrium. Okay. Read this, I'll read it to you. The reaction shown is spontaneous at 25C. Delta H for this reaction is blank. Okay, look at the answers. Equal to, greater than, or less than 0. So, what it says is it is spontaneous. What does that tell us about delta G? It's negative. So if you got a negative delta G, that means that everything on this other side, that the delta H minus T delta S is negative. Okay? So, look at the equation here. Look at the actual reaction. And tell me, what do you think is happening to the delta S? Just count moles of gas. How many moles of gas on the reactant side? How many on the product side? Ooh. What does that mean for entropy? Negative. Okay, so if you have a negative entropy, that means that the T minus T delta S portion is going to be positive, right? I want a head nod or something, right? Okay. So what does that mean the delta H has to be? Has to be negative. Okay? Now this is just saying it's spontaneous at 25 degrees C. What we learned before is we can find a temperature. We can find a temperature at which this is spontaneous. But this is saying at 25 degrees C, therefore this must be less than 0. I just hope the answer is less than 0. Hope it's number 1. Nope, look at that. I swear I didn't cheat. Okay, I think I made this up. Oops. So we got a question? Okay, I got to figure out what I did here. Okay, so I'm telling you what you got to do here. So I'm saying, what is the delta G for water at 373? What happens at 373 to water? It boils. Delta G is equal to 0 at phase changes. Better write that down. Delta G is equal to 0 at a phase change, because at a phase change we're at equilibrium. So we don't have to figure out delta G because we know delta G. Delta G is equal to 0 because you're at equilibrium between the liquid gas or the other one at the liquid solid. Okay, so anytime you're at 0 degrees with water or 100 degrees with water, Celsius, this is equal to 0. So folks, look at this equation. What if this is equal to 0? How are we going to figure out what is delta S? We just move this to the other side. And we just get this is 0. So it's going to be delta H is equal to T delta S. Delta H is equal to T delta S. Okay, you can do that math, right? Okay, so what if I tell you that delta H for vaporization is 40.7 kilojoules? What is delta S? Do it. $40.7 kilojoules. How many got that? All you got to do is take the 40.7. So you had this. You got delta S is equal to this over this. Okay? So delta H over T is this over T, 109 joules per degree mole. Okay? That's what delta S is equal to. All right? And if we're talking about moles, because that's the standard conditions, then it's just going to be delta S is equal to 109 joules per degree here. Okay? So now, folks, now I want you to use that information, the information from here, to tell me what is delta G at 363 instead of 373. 363. What is delta G? You got all the information you need right here. Who's got an answer? What's that? Oops, I don't have an answer. But yes, it is 1.0. I remember from last night. So 1.0 or something like that is the answer. 1.7 kilojoules. 1.0, 1.1, something like this. How many got that? You just used the delta S that you figured out, the 109, and then you already had the delta H of vaporization. So what is the answer, folks? Who got the answer? How many need more time? How many don't have a clue? Why is nobody raising their hand for any of those things? Yes? Okay, 1.1. Something like, is that what you get, 1.1? Yeah, you said 1.1 or 1.9? 1.1. Okay, did we get that? So folks, all you got to do, delta G is equal to delta H. Delta H was was 40.7. Okay? Right? 40.7 kilojoules per mole. And then we got the delta S, which we knew was 109. So it was 109 times 373. Okay? Now I said let's go to 363. So we had a value of about 1 kilojoule. Yes?
With the heat of vaporization...
Doesn't change. It never changes.
Okay.
It's 40.7 for water. It changes for every different substance, but water's heat of vaporization is always 40.7.
The temperature was...
Nope. Nope. It's always the same. So, folks, what does that tell us? What does that tell us about the delta G for that reaction at 363? Is it spontaneous? No. That means water doesn't boil at 363. Okay? And I guarantee if you did this experiment again and you said, well, I'm going to go to 383, guess what? You'd have a negative delta G. Okay? It makes sense, folks, okay? All right. Do this one. I was nice enough to give you the equation right here, okay? Okay, we got an answer? So all we should have to do is to plug this 6 kilojoules per mole right there. What temperature was it? What temperature would we use for that? 263, that's right. So what is delta H at the surroundings? Yep. 23 joules per degree mole. What's that? No, it's because it's the surroundings, not the system. Okay, the surroundings, not the system. It's not a trick, folks. You gotta pay attention. Is it, delta S total, which is the whole thing, which tells us whether it's spontaneous or not? Is it the system or is it the surroundings? And don't forget, in something that is reversible, folks, they're just the opposite. Okay? That if this is a reversible process, if it's plus 23 joules for the surroundings, then it's going to be minus 23 joules for the system. And that makes sense. Right? Think about it. If you go from a liquid to a solid, what's the sign of entropy? If you're a puddle of water and you go from a puddle of water to an ice cube, your entropy decreased. Okay? So the entropy would be a negative if we were talking about the system. All right. Look at this right now. Understanding conditions given the following. So my question right away is, quick, get an idea of what is the delta S. Is it positive or negative? Okay, so we've got one gas here, we got, it's negative. So you already know that, okay? So I'm not sure that's going to help you, but at least you know it. Okay, and this is what's given to you. Delta S is equal to that. Delta H for the reaction is that. And don't forget, delta S of the surroundings is equal to, this is what we just saw, okay? So the question is, what is the, is the combustion spontaneous? Oh, yes, it says spontaneous. Okay, good. So you want to write that down because I'm going to go to this one. Okay, need that again? Write those two numbers down right there. This and this, okay? And once again, this is so you can figure out what the delta S of surroundings is. This is just to help you, to guide you. This doesn't mean you should just look at this and then you say, okay, I understand. Here was the delta H. Okay, and it's been converted to joules. Once again, you cannot leave, because this is going to be in joules. Something's usually in joules. Yeah, that one right there was in joules. So, you can do the surroundings one. This is the delta S of surroundings is equal to that delta H over T. That's what that is right there. And what we're saying is that is the value right there. About 4,000 joules, okay, per degree for the delta S of surroundings. So the question then is that what is the delta S total? Well, we got that value from this. This value I gave you right there. So you just add them up, okay? And you get this value right there. So the delta S total is equal to that. What does that tell you about whether it's spontaneous or not? Absolutely. Don't forget delta S, if the delta S total is a positive number, then it's spontaneous. That's the definition. So there are a few things you have to kind of memorize, all right? This, once again, folks, I'm not good at this. I'm not good at looking at something and telling whether the actual universe got better. Now, if you give me a number, I'm good at telling you whether it's spontaneous or not. That's why delta G's. That's why I like delta G's. Okay, do this one. Okay, we done? Oh, gosh. So how many got this for the delta S? Still working, okay. You guys got to get those fingers working. Get that calculator. You got to know where the buttons are. Know where that LN button is. You still remember where that factorial button was? No. Okay, I'm done. You guys are you done? So, how many got that delta S is equal to this? How many aren't done? How many are clueless? Okay, a lot of you. All right. So how many remember this? Okay, this was something, I gave you 3 equations. Okay, one for volume, one for temperature, and one for pressure. That I said you got to know what this is. Okay? So if you don't know those, folks, you better start committing something to memory, okay? This is one of them. For volume, it was delta S is equal to NR log V2 over V1. I gave it to you. So why is it we can't get this? Raise your hand if you got this answer. Raise your hand. All right, well, good. Half of you got it. I'm not sure why the other half didn't, since I gave you everything. So, delta S is equal to a 7.6 joules per degree mole, or per degree, okay? Now, if we need to know what the delta S of surroundings, and the delta S total is equal to. The clue, folks, the clue is, in this first case, it is isothermal and reversible. What does that mean delta S total is? 0. Okay? So if delta S total is 0 on something that is isothermal and reversible, then what must the sign of the surroundings be? A negative 7.6. So for the reversible isothermal, folks, and this would be like an easy multiple choice where you don't have to do any work. You would just, if I said that the delta S of the system was plus 86.2 joules per degree, it's isothermal reversible, I could ask what is delta S total, so it has nothing to do with the numbers I gave you. Or I could ask you, what is the delta S of the surroundings? So easy answer folks when it is at equilibrium and reversible. So when it's not, okay, when it's not, we do this. We've got that Q is equal, remember that this was the work, right? Work was equal to, remember the minus nRT log K, or log V2 over V1, okay? Q surroundings is equal to the negative Q of this, so that's why we're using this work function right here to figure out the heat. Okay? So we figured that out, that's 0. Now this one. Q is equal to 0 in that non-isothermal one. Q is equal to 0. So what is 0 over T? 0. So if that part is 0, then we just have the surroundings is equal to 0. And therefore the delta S total was just the system's entropy plus nothing. So we have a positive 7.6. This is a little bit of a tough problem, okay? Just so you know, I consider this one, it's pretty detailed and all, okay? So this would be probably like a 10-point question on an exam. Do this one. We've already done it like one just like this, except it was not at the fusion, it was at the heating, at the vaporization one. So you should be able to do this really quick. Stop. Okay. Had to wake up, there's some people sleeping. So, look at the question. What is your gut feeling? What am I really asking here? What am I really asking? Okay, yeah, I'm asking for the delta G, I think. Yeah, calculate this. How many got an answer for 10 degrees? Okay, what do you get for 10?
Negative 216 joules.
Okay, that's wrong. Who got, what'd you get? You raised. No? Yes? Say it again?
5.79 times 10 to the 30.
I don't know if any of these, at least yours is positive. Okay, folks, those who gave me a value of a negative, The question is, I have ice. No, I have liquid water. I have water. What's that? Oh! Okay, just testing you. Okay, you're right. You're wrong. Okay, so I'm sorry. So I guess what I was thinking was are we going to, at 10 degrees, are we going to have liquid water become an ice cube? The answer is no, but obviously you're smarter than I am. So if you have an ice cube at 10 degrees, sure, it's going to be spontaneous. So it's going to have a negative delta, or delta G. Sorry. Does that make sense? So once again, look, if you read a little bit better than I do, you'll know what the question is asking. And then you'll be able to have a clue as to whether the sign should be positive or negative. Okay? So now do the one at 0 degrees. At 0 degrees, let's say you didn't have a calculator, and I wanted an answer in 4 seconds. Thank you. He says 0. Remember phase changes. At phase changes, delta G is equal to 0. Okay? So at 373 and at 273, now you're going to get a little value, okay? How many actually got a delta G at 273? Right. Now what I want you to do is use the correct value of 273.15 for temperature. And now what's going to happen is your delta G is going to be about as close to 0 as you can be. Okay? So, sorry for the mistake that I made. I thought I was asking something else. Okay, so you got this value, which is the correct value, which I said was incorrect. Okay, at 0 degrees, we got that. Okay, do this one. So, folks, on the exam, there very possibly is going to be a table that's going to have delta G's, delta H's, delta S's, okay? From that, you would then go and find all of these things, okay? The delta H formation, the delta S, the molar delta S, molar delta S, and the molar delta S for these things, okay? I'm going to be a nice guy right now and give you. So write this down. Write that down so that you've got it so that I can go to the next page. So looking at this, folks, what do you think the entropy is going to, sign of entropy? What's the sign of entropy likely to be? Positive. We go from 1/2 of a mole of a gas to a whole mole of a gas. So chances are pretty good that when you do all this stuff, that the entropy is going to be a positive. Okay, so turns out that you just find this from the book, that the delta the delta H of HI is this. Okay, we don't have to worry, folks, about the delta H of this or this because these are their natural states. Okay, delta H doesn't cost us anything. Hydrogen gas is H2 and I2. Now, if I asked for just an H, that'd be different. But in this case, we had 1/2 a mole of H2 and 1/2 a mole of I2 going to this. So these have no delta H in formation, okay? So the only thing you got is this 2648. Got that right out of the table, okay? Here are your delta S's. And this is products minus reactants. Do it. Plug those things in, folks. You can never practice too much. So if you write those 3 delta S's down, then just plug it into, I've already done it for you. There it is. Okay, how many didn't get that yet? Oh, jeez. Okay. Now, once again, folks, I don't care, well, I don't care if the answers that you give me are in joules or kilojoules, okay? So we have converted this 82 joules to this many kilojoules. So we've got this many joules right here, okay? This is how much change in entropy there is. And did we say it was going to be positive? Yeah. So it is positive. I didn't lie. So you have to have the entropy. Now, so folks, once again, the delta H, the heat, oxygen doesn't cost you anything, hydrogen doesn't cost you anything. But for entropy, everything's got entropy. Everything is entropy. So everything is going to be listed as a value for entropy on those tables. So, from the table you got this 2648 in kilojoules, and then minus T delta S, 298 times this. So the delta G is equal to this value right there, okay? So, is delta G positive or negative? Is it going to be spontaneous? No. You can look right at this number and say absolutely not spontaneous. Just like an ice cube at 10 degrees below 0 is not going to melt. Or water at 10 degrees above 0 is not going to melt. It's not going to become an ice cube. So did we get this? People are looking a little bit glassy-eyed. Who didn't get this? How many of you think you understand? Folks, you don't get it the first time. Okay? This is something you got to practice, practice, practice. Now, folks, this was a question right out of the text, out of your text, okay? So when I give an example like that, like this, you can just turn to your book and it is example 8.15, okay? Now, on this one, folks, we had to figure out what the delta H's were and the delta S's. Okay? But in that table 2A, also, they give delta G's. It's kind of cheating, but they give delta G's. Okay? So, in this equation right here, this reaction right here, you can just go to that appendix and look at what is the delta G for NH3, for O2, for NO, and for water. Okay? And I can tell you what one of them is going to be. But look at this. What's the entropy? What's the sign of entropy going to be? What is the sign? I'm going to point to somebody at the very back. How about this lady right there? You. You, yes. What is the sign of entropy? Positive or negative? Positive, she says. I agree. There's 9 molecules on this side, 10 molecules on that side. Now, folks, this works. I mean, each molecule has a different kind of entropy. Okay? This works when you have, you know, a significant difference. Okay? This is a 10% difference. You got 10% more of these than this. Okay? If instead you'd have had 100 over here and 101 over here, then maybe it's not quite the same. Okay, because some of these molecules can actually have more entropy than these. So, rule of thumb is that if you got like 10 molecules on one side and 11 on the other, then the one that has 11 has more entropy. Okay, Appendix 2A. Here are your values. Okay, so this is how you'd set it up. Products minus reactants. Okay, so the equation, did you guys write that down? Did you write this equation down? Write that down, folks, because I'm going to switch off of this and you're going to have to figure out what is products minus reactants. Four NH3 gas plus 5O2 gas goes to 4NO gas plus 6 water gas. 4 NH3 gas plus 5 O2 gas goes to 4NO gas plus 6H2O gas, okay? And then we go to this. So delta G, products minus reactants. So if you look at that equation, on the product side, you had 4 NOs, you had 6 waters, minus 4 NH3s, and 5 oxygens, okay? So the table says that for NO, 86.55 is the delta G of formation. The delta G of formation for H2O is minus 228.57, minus the delta H of delta G of formation for NH3 is minus 16.45, and there is no delta G of formation for oxygen because it's free. So you work through this math and you come up with that the delta G is equal to about minus 960 kilojoules. Spontaneous? Heck yes. So folks, if you are given delta S's and delta H's, then you can figure out delta G. Or you can, if you're given delta G's of formation, then just use them. It's a whole lot easier. Do we understand this? I don't know. Okay, let's kind of switch gears here. Take a deep breath. You don't have to write this down. Okay. This is like a very easy multiple choice question for me. Which reaction of these three belongs to the plot delta G versus T? Delta G and T. Don't answer it, just think. Look at that plot right there. Okay? And for those of you who aren't good at reading plots, this is 0 for delta G. This is 0 for delta G and 0 for temperature. This is negative delta G, and this is from 0 out to some large temperature. So what can we say about which one of these this belongs to? What does it say? Okay, there's really nothing we can say, at least that I know of, that we can say about what the, how to figure out which one of these has a big negative delta H, okay? I wouldn't know how to do that. What's the only way that we can figure this out? Entropy, yes. We've got entropy. What is happening with temperature? What is happening with temperature, folks? As we increase temperature, this direction, what is happening to delta G? Delta G is becoming positive, right? So what does that mean must be the case for the minus T delta S part? Okay, so look, let's say we go to absolute 0. Absolute 0, okay? Entropy is equal to 0, right? We can't do it, but let's just say we can today. So where on this plot is absolute 0? Right there, okay? Temperature coming this way. So we would go down to right about there, okay? If this line were to continue down, we go right about there, all right? So what does that tell us about delta H? If entropy is 0, then delta G is equal to delta H, right? If that term minus T delta S is like tiny, 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 then the delta H wins. Look at this. Is this a negative delta H or a positive delta H? Negative, folks. Wake up. This is a negative. Delta H in this reaction, in one of these reactions, has got to be negative. And pretty dadgum negative, okay? But I can't tell delta H from these things. I can't look at an equation and tell whether it's a reaction, and tell whether it's a delta H is a positive or a negative. So I'm going to look at the entropy. Okay? So what must the sign of entropy be? Folks, look at this. Delta G is increasing with temperature. The only way to make that happen is to have a negative entropy, because a negative times a negative is a positive. So what this means is that at some temperature, low temperature, that minus T delta S part isn't contributing too much, and therefore we're in the negative. But at some temperature, it becomes positive. That means that the delta S has to be negative. Delta S absolutely has to be negative. How many understand? How many don't understand that? I mean, okay, never mind. Don't raise your hand. I don't want to know. So, play with that equation enough, folks. You should know delta G is equal to delta H minus T delta S in your sleep. Forwards, backwards, whatever. Okay? Know how if you change this, this changes. If I change this, this changes. Okay? So in this case, we, I think, have decided, at least half of us, that this must have a negative entropy. So which of these three should have a negative entropy? Okay, let's look at this one. How many gases on the left? How many gases here? So we can't really say much about entropy there, can we? Okay. Doesn't mean that entropy is zero. It just means that it's pretty darn close to zero. Okay. And then this looks like it's got a pretty steep slope. So we can rule this one out as being sort of, we can't tell. This one, what do we have? We have how many gases? A half. How about this one? So folks, for those of you who couldn't hear your classmates, this has more entropy. Equation 2 has more entropy because it's got a half of a gas molecule on this side, and number 3 is a negative entropy because we lost a gas, right? So number 3, folks, is going to have a negative delta S. So that's the only one that would give us this kind of a curve. Okay? If that logic scares you, go over this and over this and over this. Okay, this is just some examples, okay? Look at number 1 there, okay? What do you think is the sign this is the only one I can look at and tell whether it's going to be positive or negative. What is the sign of entropy in the first reaction? Positive. Perfect. How about the next one? Negative. Next one. Says positive. I guess because we're going from one thing to two things, but it's not very, entropy-wise, it's not very big. So these cases where we have a positive and negative means that, depending on the temperature, we can have a positive delta G or a negative delta G. Okay. Which is the correct plot of delta G versus temperature for the reaction water liquid to water gas? Okay, water liquid to water gas. And this is the triple point. Triple point is where you have all three of them together. You can have a little bit of gas, a little bit of liquid, and a little bit of solid. Okay, so we're right here. What is the delta G versus temperature for that plot right there? Liquid to gas. Which one do we think? So if we're going from a liquid to a gas, is that good entropy-wise or not? Liquid to gas? Sure. So we know that we're going to have something. Remember how we had the, so what that means is that at some temperature, we can make the delta G go negative. So which one does this one work? No, as we go negative, if we increase temperature here, delta G goes positive. So we can get rid of this one right off. So we're either this one or this one, okay? So which one do we think it is? That it's always a negative delta G, or that it at a certain temperature will become? Okay, now this is where a little bit of like your own intuition. You know, we're looking at liquid, solid, and we've done several problems today with water. Okay, what we know is that that liquid to gas happens, but it only happens at a certain temperature, right? It doesn't always want to boil. Okay. Right? I can have water at 15 degrees, okay, and it's got a positive delta G. It's not going to boil just sitting here, okay? So that's how you knew that it had to have a delta G that was positive at some point. This one has never has a delta G that's not a negative. Okay, so listen up. My back is sore. You guys are starting to close up shop. Example 816 is given in the lecture notes. It's got the answers. Doesn't seem to want to change. My suggestion, folks, is to study the lecture notes through slide number 50. Okay, slide number 50. So we're going to, on Thursday, may finish a little bit more of this up, and then we're going to move to chapter 9. So you need to read about the first 15 pages of chapter 9. I'll also send some extra discussion questions that'll have some more of this delta G stuff.